Hello, everybody. It's time to learn about linear programming. So, linear programming is a topic that takes a really long time to do one problem, but each individual step of it really shouldn't be that difficult. And of course, that's me saying that who's done it a few times, but you should be able to do things like write functions, draw or graph lines or graph inequalities, which would just be lines that are shaded above or below them, and plug things back in. That's really all you're being asked to do here, but one problem will take you probably 15 minutes, just so you know. The goal of linear programming. All right, I'm on pages 714 and 715 of your book, if you can see this here. And the goal of linear programming is basically to optimize what the maximum, what the best conditions are to meet your goals. So in many applications, we want to find a maximum or a minimum value that helps us meet our goals. So for example, in many businesses, the main goal is to maximize profit. Not always. Sometimes it'll be to minimize something else, maybe minimize spending. But we're going to work on trying to figure out how to maximize the profit. So if you keep this page open while we work, that might be helpful. Problem we're going to try to do is example 7 on page 714. Dovetail Carpentry Shop makes bookcases and desks. Each bookcase requires 5 hours of woodworking, 4 hours of finishing. Each desk requires 10 hours of woodworking, 3 hours of finishing. Each month, the shop has 600 hours of labor for woodworking and 240 hours of labor for finishing. The profit on each bookcase is $40 and on each desk is $75. How many of each product should be made in order to maximize the profit? Okay, that's a lot of stuff. I'm going to attach pages like this for you to print out if you like, but you can just do this in your notebooks if you don't want to print this out. But this kind of captures everything that's going to be involved in finally finding what the best advice for this carpentry shop is. We're going to give them some advice about how many desks and how many bookcases they should create in order to maximize their profit while staying within their constraints. All the things they said about how many hours they're allowed to work. We want to make sure we don't ignore those. We want to stay within those, but we still want to maximize profit. Okay, so the first thing you look for is the objective function. The objective function represents whatever the overall objective of your business is. So you can usually find that in the last sentence where it says the question. So what do they want to do? What's their main goal? They want to maximize profit. Okay, so we're going to try to find the maximum profit. I'll keep that in mind. The objective function then has to calculate profit. So I'm going to say, let's see, where do we find the profit? Okay, it does say the profit on each bookcase is $40 and on each desk is $75. So if we write an equation like this, 40x plus 75y, that should relate to the profit made from books. Sorry, that went away. Bookcases versus the profit made from desks. Okay, and so this actually needs another variable for the total. There's no total yet here. And so it's profit, so we'll call it P. It's actually going to be like this. It's your first time seeing a function notation, where there's more than one input. So this is going to be P of x comma y, meaning that your profit depends on two things. The input of x, which is the number of, we should write it here, the number of bookcases they should make, and y, the number of desks they should make. All right, so we've got our objective function. We're going to hold on to that and use it at the very end. We're not going to use it for a long time here, so it's just going to sit. What we're really going to use for most of the time here is the inequalities, aka the constraints. So what other constraints did we read about? It said that they only have 600 hours of labor available for woodworking. That's a constraint. That's saying that even though it'd be obviously best to make an infinite amount of desks and an infinite amount of bookcases, we can't, because the amount of labor that we have is only 600 hours for at least the woodworking. All right, let's read where else it talked about woodworking. 5 hours of woodworking, 4 hours of finishing, 10 hours of woodworking. Okay, so it's 5 hours for the bookcase, for each bookcase, 10 hours for each desk, and that has to total to no more than 600 hours of labor. Here's what that inequality is going to look like. Does that make sense? So this stands for the woodworking. The total number of hours spent on bookcases plus the total number of hours spent on desks is not allowed to exceed 600 because apparently that's all the hours they're allowed to make their employees work. Okay, there's something really similar happening with the finishing. I think it's 4 hours and 3 hours per bookcase and per desk. And they are not allowed to exceed, if you look back at page 714, 240 hours on the finishing. And if I look through, I think I've used all the numbers in the paragraph, so that's it for the constraints, except for the fact that there are always 2 more constraints you should use for problems like this that don't show up in the words, but they're just kind of logical. So you want to make sure one of your constraints is that X is non-negative, meaning you are not allowed to use a negative amount of bookcases, obviously, and Y is non-negative. Okay, so now that you've got the constraints, you're supposed to graph all 4. The bottom 2 should be sort of easy to figure out how to graph. X is greater than or equal to 0, Y is greater than or equal to 0. I actually recommend graphing X equals 0 and Y equals 0 first, and then shading later, but remembering which direction you're going to shade. The next 2, which are a little bit harder to graph, are still XY equations, so you know how to do this. You just have to put it in a form you're familiar with. So let's go ahead and put it in Y equals mx plus b form. And in fact, it's going to be Y is less than or equal to mx plus b form, but whatever, we'll go with it. So we'll do that real quick. Subtract 5x from both sides, and I'm going to put it here just so it sets me up more nicely for Y equals mx plus b form. Divide by 10, so it's going to be Y is less than or equal to negative 1/2 x plus 60. Great, so that is just a different way of expressing that first equation. And then we can do the same thing with the second equation. So now we know the slope and the y-intercept of each of those 2. And I already graphed it for you. It turned out when you started to graph these 2, you needed to be scaling by something else because you can't fit y-intercepts of 60 and 80 on the graph otherwise, so I scaled by 5, and I did my slope normally, which is fine to do as long as you scale it the same on the x-axis and the y-axis. These little red arrows that I have everywhere, they represent which way I'm going to shade because it said y is less than here. So you read all of these from the y's perspective. Y is less than, that means I need to go beneath a particular y coordinate. Pick a particular y coordinate and go beneath it. And then same thing for the other equation. Pick a particular y coordinate and go beneath it. So all the constraints are lower, lower, and this one is more and more. Okay, that's why I had these red arrows over here and over here. So overall, where is it below both of the angled lines, but above x is equal to 0 and y is equal to 0? Turns out this is that region. This region is known as the feasible region. I'll write that down over here. Vertices of feasible region. So our next step, well, we need to understand what this is. This region represents all of the XY combinations, all of the combinations of desks and bookcases that could be made that do fall within, and they still honor all 4 of these constraints. It's not about the profit yet. We haven't done that yet. We have not graphed the objective function. We haven't played with this in a while. We'll get there soon. But first, we're going to acknowledge these are all the places that x and y fulfill all 4 constraints. And it turns out that the vertices, which are the 4 most extreme points, are either going to represent, like, there are 4 vertices here, and one of them is going to represent the minimum profit, and one of them is going to represent the maximum profit. So I'm going to write down all the vertices I see. I see 0, 0. I see 0, 60. I see 60, 0. And this one right here looks like it's not on a grid line. It looks like that one might be harder to find. This is why this is in chapter 8. What did we just do at the beginning of the chapter? We solved systems. Systems or equations, substitution or elimination, are a way of telling you where the intersection of two lines are, where x and y meet, where they happen to be the same in two equations. So we're going to use substitution or elimination to find that last vertex of the feasible region because it didn't fall on a grid line, so it's not obvious. What you do is you take these two equations, I'll erase everything else, and you figure out where they meet. I think this looks like a great opportunity for substitution. I'll put this one instead of that y. Also, it's not going to really be about inequalities here when you're finding the intersection because we don't care about where they're greater than each other. We care about where they're exactly touching, where they're equal to each other. Okay, so negative 1/2 x plus 60 equals negative 4/3 x plus 80. And let me go ahead and add 4/3 x to both sides. I'm cheating and using my calculator, and I'm finding out that this is 5/6x plus 60 equals 80. So 5/6x equals 20. So if I multiply both sides by 6/5, I get x is 24. If I want to find out what y is equal to, I can put this x back into either of these two equations. I would like to put it into this one. So y equals negative 1/2 24 plus 60, that's negative 12 plus 60. So y is going to equal positive 48. So it turns out 24, 48 is that last vertex we were looking for. And then what are we going to do with these vertices? We don't need a fifth one here. What we're going to do is we're going to find their value when you plug them into the objective function. The objective function, finding out where you can make the most profit, is finally about to come back. So if I plug 0 in for x and 0 in for y, that's saying the total profit of producing 0 bookcases and 0 desks is $0, which is obvious. So that's clearly not the maximum. What that's actually going to represent is the minimum. Remember, one vertex is going to be the max, one vertex is going to be the min. The others won't really give me that. So I'm going to keep filling these in, and I'm going to keep calculating what these are. I'm going to pause and come back. And by plugging all these in, I figured out that this last one's going to produce the maximum profit. It beats out the 60 desks and no bookcases by a little bit. Okay, so there it is. We found it. Of all the possibilities that fulfill these 4 constraints, this one is the one that gives us the best profit for the dovetail carpentry shop. So I'm going to write that its maximum value, I don't care about the minimum, is 4,560. And then for your final answer, you want this to read like a recommendation. It has to be a full sentence. It has to include the important numbers, and it reads like a recommendation to the company. So I'll write to make a maximum profit of $4,560. You should make 24, what did X stand for? Bookcases, and 48 desks. Okay, the end. These are really long problems, so if you're a little bit overwhelmed, that's okay. Just take your time. Just try to get one step at a time, and good luck. You can do this.